give you now a better example. So let's consider this other example. So this example, what do we have? We have, again, a grid world, but now it's 4 by 4. So we're going to have 16 different cells, right? We have two terminal states, so state 0 and state 15, right? If we get anywhere there, we are going to keep on getting reward 0, and we stay there forever, right? So these are where everything is going to be over. The episode is over, right? And now you start from one point, one state in this grid world, one of the cells, and then you can move exactly as before, up, down, left, right. And then each time that you move, you're going to get a reward -1. And this -1 doesn't matter. If you hit the wall, you still get -1, right? Each action you do, you get -1 unless you arrive to the terminal state. OK? Everybody's cool? So eventually, what you're doing, you want to start at one of the cells, and you get to the corner, which is, if you are at 11, for instance, the right choice is to just go down, right? Whereas if you're at 1, the better choice is to just go left, right? End up with that terminal state, right? Everybody's cool?
Do you have to go from 0 to 15? Or
No, 0 and 15, both of them are terminal states.
Oh, so I can go 0, 1, 0.
You cannot get out of 0. When you are at 0, you're over. Yeah. It's a terminal state. You're going to stay there forever, right?
So we start in some random position?
Right. Some random cell you start, and then you want to just move like optimally, like you take the shortest path toward the corner.
And the shortest path to whichever corner is closer to you?
It's either 0 or 15, depending on the cell, right?
Yes.
Yeah. So if you're at 11 or 10, the shortest or nearest corner are going to be 15. But if you're at 1, then it's going to be 0, right?
That makes sense.
Okay. No worries. So everybody's cool? Now, first, let's consider the policy iteration. How are we going to do policy iteration? We're going to start with some random. I'm going to do a total random policy, meaning that I just consider this policy that at every single cell, with the same probability, I'm going to move in one of the directions, right? So probability of going up, down, left, right is 1/4, right? So this is a completely random policy, and the thing that I'm going to do, I'm going to set all the values to be 0. Eventually, if you set all the values to be 0, is a safe choice always, right? Because by default, the terminal states are 0. Anything else could be any number, right? So they are all being 0, right? So I'm going to start with the value, complete value 0, right? And what I'm going to do, I'm going to do policy iteration, meaning that I have started with this pi. This pi now is the complete random policy. The values v pi, which I start with, is complete 0, that table of complete zeros, right? And now I start to do dynamic programming to find out what is the value of this random policy. OK? Cool. So I'm going to do this, and I start with this one. Now, you do 1 iteration, 2 iteration, you keep on iterating. If you do 1 iteration, every single cell is going to get updated by -1, right? Because value, for instance, look at this guy. The value at this point, at this cell 1, is 0, right? Now, when you want to find out what is the value for the next iteration, you're going to take all of those zeros, right, and add them up with the immediate reward that you get playing your policy. When you play your policy, it doesn't matter which direction you go. You always get -1, right? And the expected value of the next cell is still 0. So you're going to add up -1 to that 0, right? So any guy in between going to get -1. Just the terminal state is going to remain 0, right? And you keep on iterating. So you go on, maybe one more iteration, and you keep on going till you have enough iteration. You see that your values are not changing, OK? So when you get to this guy, to this table, you see the values are not changing. If you start again from this value, so you take it as v pi k, and you give it to the Bellman equation, what you see at the output of Bellman equation is, again, the same values, right? And this means that these are the values of this random policy. Everybody's clear? Right? So I got this one. This is the value of which policy? Which policy? Random policy. The policy that I just move in all directions randomly, right? Now, what should I do next if I'm doing policy iteration? Improve the policy, right? So what I'm going to do, I'm going to just go in every single cell and see what is the action whose action value is maximum, right? So let's do it for one of them, just to make sure that you understood this. So let's consider cell 1. Do you see what is cell 1? Do you see what is cell 1? So it's the one which is on the first row, second cell. Okay, that is cell 1. Okay, so now let's look at that one and see what is the action value when we are playing with this random policy, right? So I want to know what is Q pi 0, okay, at this particular 1 when I do one of the actions. So let's first consider the action up. Okay? Let's consider that one. Okay? Now, how can I write it down using Bellman equation? If you use the Bellman equation, this is going to be the immediate reward that you get at this particular cell 1 doing action up plus the expectation with respect to pi of the value in the next cell, right? So, okay, maybe I can't take it up. The expectation of the value of pi in the next cell, given that I am in this particular cell 1 and I am doing action up. So this is what you're going to get out of the Bellman equation, okay? Now, what is the immediate reward when I am in 1 and I move up? What's going to happen? -1, right? It doesn't matter which direction I go, I always get -1, right? So this guy is -1. Now, if I am in cell 1 and I move up, what's going to be my next state? What's going to be my next cell? 1 again, right? Because I hit the wall, I remain there, right? And if I keep on playing randomly after that, what is the value that I'm going to get? Look at the table. -14, right? So if I play with the random policy, the value that I'm going to get -14 in cell 1, right? You see it? This is -14, right? This guy. Everybody sees that? This is the value of cell 1 when you play randomly, right? Everybody's cool? Okay, so what would be this expectation then? If I am in 1 and I go up, is there any confusion? Is there any randomness? No, I'm going to end up exactly 1, right? So actually, I don't need this expectation anymore because it's not like I'm just jumping from one cell to another, right? I'm going to remain there, and this value is -14. So eventually, this expectation simply is value of pi at cell 1, which is going to be -14, right? So now what is the action value of cell 1 when I go up? -15, right? So I'm going to keep it -15, right? Okay? Everybody's cool? Now, let's just consider another one. Any other color? No, it's weird that, oh, at least we have no chunks here. Okay. Now, let me just write it down here for you. So Q function of the policy pi 0, this random policy that we started with, at cell 1, when I go up, is going to be -15. Okay? Now, let's just replace this one by another action. So let's say that this is the action. I'm going to go left. Okay? Now, I want to know what is the action value. So I'm going to clean this up here, and then everything should be the same. So it's going to be the immediate reward at 1 when I go left. The expected value of the next cell when I am at cell 1 and I go left, right? Now, what is the immediate reward if I go left? -1 again, right? What is the next cell if I go left? If I go to cell 0 and I play with my random policy, what's going to be the value? Because it's a terminal state, right? So it's going to be cell 0. The value is 0, right? What is then the action value when I go left? And I go left, that is -1. Great, all right? Now, can you tell me what are the two other action values? Do you have any idea? Just look at the table. I guess now you can guess. What is the action value if I am at 1 and I go right? -21, because if I go right, I'm going to go to the cell 2, right? And that is giving me value -20. -20 plus 1 minus 1 is going to be -21. What is Q pi 0 when I am at cell 1 and then I go down? What is going to be? -19, right? 18 plus 1 is going to be -19, right? Now, looking at these action values, what is the optimal action to do? Just go left, right? Because it has the maximum value, right? Among all of them, right? So we started with random policy. That random policy gave us a bunch of values for the random policy. But what we obviously see is that this random policy, given those values, is not optimal, right? So what is the right improvement is that when I am at this cell 1, I move left instead of doing any other action, right? So I'm going to take this action, right? I'm going to take this action, right? Right? Okay. So let's see. No, I'm very afraid. Maybe it's not the right solution. So let's see. So I need to improve, right? Line 6, I want to improve. So I had the values that I computed, this table. I give it to the policy improvement. I do exactly what we did on the board, and then we improve. So this was the first policy, and okay, we were right. Okay, no worries. So for cell 1, the right action is to go left, right? And you can see it on the values here for everybody, right? So when you see, for example, when you are here, you see that if you move here, you're going to get, I mean, this is the next value, which is -14. But if you go here or down or up, all of the values are less, right? So the right choice is to go left, right? So when you if you update this policy by this policy improvement, this is going to be your new policy, okay? Now you have your new policy. You're going to take it, again, put it inside the dynamic programming algorithm, right? Meaning that you start with a bunch of values. We use now this particular policy to compute the Bellman equations, and we keep iterating till the value function converges, right? So if you we get again back to line 5, but this time instead of using the random policy, we use this improved policy pi 1, right? So you keep on doing this. So you could start from complete 0. But typically, as I told you, the best thing is that you set the initial values to be the values you computed with your previous policy, right? So these were the values you just computed for random policy, and then you can keep on iterating, right? Keep on iterating till you end up with this new value function, right? Now, this value function makes sense, right? If I do this particular policy, sorry, this is the policy pi 1, right? If I do that policy, this is -1, this is -1. Here is -2 because I either go up or go left and then go to the terminal state and so on, right? Now this is the correct value function. Now that you have this correct value function, you could again improve your policy. But as a matter of fact, for this dummy example, if you do improve it, you're going to see that pi2 is going to be exactly pi1, meaning that your the algorithm you found, policy you found, it was optimal policy, right? And the policy iteration algorithm has stopped. Questions? Everybody's clear? So you got the idea how the policy iteration works, right? Cool. So that's the case, but what you can do, you can also use value iteration, right? If you want to use value iteration, again, the thing that you're going to do, you're going to start with some initial values. But these initial values are not the values of a specific policy, right? They are the values that you initiate for your optimal policy, right? And then you're going to go ahead, so you're going to say that optimal value for all cells are 0, and then you are going to just iterate with the dynamic programming, meaning that you just put it inside the Bellman equation, you compute the next one, and so on till you converge, right? And when you do enough number of iterations, you're going to see that you get these values, right? Out of these values, again, like what we did on the board, we can find the action value, right? And then out of the action, this is the optimal value function. Then you're going to get the optimal action value. And then out of that optimal action value, you can just write down your policy, which is going to be exactly the same thing. Everybody's cool? Questions? No question? OK. So if you got no question, now one thing that you might ask me is that, well, if we just do value iteration, it seems to be less complicated, right? Because for value iteration, you just need to do this dynamic programming loop once, right? You don't update your policy, correct? So you have your no policy, you just find the optimal value, and then once you found the optimal value, everything after that is not iterative anymore, right? So it might come to your mind, it's not wrong. I mean, in many simple examples, this is really the case, but this is not generally correct, okay? And just to show you why this is not generally correct, so let's think about the particular example we had. We had this policy pi 0, right? And policy pi 1. Policy pi 0 was the random one, pi 1 which was the improved one, right? And then when we had to first evaluate this policy, say for example k1 iterations was the number of iterations we took to get into that policy, that value function. So this is the first recursive approach. And say k2 is the one which we took to just evaluate the second policy, okay? Meaning pi 1, right? Now, k1 plus k2 is the total number of iterations you have done in this whole algorithm, policy iteration algorithm. k1 for the first one, k2 for the second one. And one thing that you would see in practice is that this k2 is going to be significantly smaller than k1, because when you want to just evaluate policy pi 1, you start with the values of policy pi 0, right? And that is a very good start point, so you're going to converge you much faster, okay? So typically you see that k2 is significantly smaller than k1, but in total you can say that k1 plus k2 is the total number of values that you have taken, right? A number of iterations that you have taken. Now, if you want to do the value iteration, well, you probably do k star iterations, right? So you start from all values being 0, and then you iterate using optimal Bellman equation till you converge, right? Say that this number of iterations is k star. There is no reason for k star to be smaller than k1 plus k2. You see it, right? There is no reason, because one policy might be very simple so that the convergence is happening very fast, whereas the optimal policy is complicated, and then it takes time to converge, right? So there is no reason for k star to be same as k1 or k2 or even less than that, right? So it could be the case that, for instance, k star is more than k1 plus k2. It could happen, right? But if you think about a kind of a bit generic MDP, and then you think about like doing enough number of iterations for every policy evaluation, then this is typically the case that k star is a bit smaller than the summation of those iterations you do within the policy iteration, okay? This is typically the case. But in terms of the order doesn't change. So the order, like, by order I mean how it scales with the number of states that you have or the number of actions that you have. It doesn't change in the order, okay? It's going to be the same. Meaning that if you have a very big environment, both of them going to take roughly the same amount of time to converge, okay? Now, this is the key point. So there is no reason that this value iteration is strictly simpler than the policy iteration. But typically in practice, you see such an observation, okay? Now, one thing that comes to your mind then is that, okay, if they are having the same order of complexity in terms of the number of, or the time that it takes, then why should we do policy iteration, right? Why should we just take a policy, evaluate it, improve it, again evaluate it and improve it? Why we don't stick to one giant loop for evaluating the value? Well, there are a bunch of reasons, but the most important reason for that is the fact that we cannot really converge in those loops. So what is going to happen in practice if you are not having a dummy example like what we had here, if you have a real environment? Then the thing is that when you go inside that loop, which is just iterating, doing the dynamic programming, it's not going to converge exactly. So there is no point where you see exactly the updated value is the same thing as the previous value. So it's going to always get better and better and better, right? But this improvement, the new values that you compute are getting closer and closer, right? So what you need to do at the end of the day, you need to terminate it at some point, right? So you're going to say, I'm going to do dynamic programming for 100 iterations, 200 iterations, right? When you terminate it, the values that you take out of that loop are not the exact values, right? They are estimated values, right? And then if you just keep the giant loop for the value iteration, you are going to estimate the optimal values, right? But that estimate could be a poor estimate, right? This could happen. If really the environment is complicated, then you could have a poor estimate. Whereas if you start from some dummy policy, like for example the random policy, this could be the case that it converges better, right? So the values that you get out of that iterative approach, the dynamic programming, are better estimate. And since you have a better estimate, you can improve your policy more concretely. And the next policy, again, is going to converge better and better and better, right? So the main reason that policy iteration could work better than, or might be preferred in some situations, is simply numerical. Because numerically it could be more stable as compared to the value iteration, right? So if your value iteration loop is going to really converges to the optimal value, that's okay. But in practice, most of the time it does not converge. You need to terminate it at some point, right? And when you terminate it, you could get looser kind of approximation as compared to what you would get with policy iteration, okay? So this is the reason that when you really do approximative computation, then people prefer to do policy iteration because it could give you a better estimate and eventually ends you up with a better policy, right? So moral of the story is, so if you do value iteration, your algorithm might stop faster. You might take less time, not in order, but like slightly less time to converge or get your output out of the algorithm. But that guy might be less reliable numerically as compared to what you get with policy iteration. So this is a trade-off you might need to consider when you are just implementing. Okay? Question on that? No question? Okay. So if you got no question, now one thing that people would like typically to get out of this policy and value iteration is what we call it generalized policy iteration. And that is exactly the same policy iteration as we had. The only difference is the numerical, the computational or implementation aspect I just said. So in practice, when you do policy evaluation, that evaluation loop, this loop which you have in line 5, if you have really policy evaluation algorithm, this is not necessarily converging, right? Maybe you need 1 trillion iterations till it gets converged, right? But you don't want that, right? Because you want to get this, improve your policy, do it again. If each time you want to take, I don't know, 10 to the power 10 different iterations, then it's going to take forever, right? So probably what you want to do, you want to just give it a maximum number of iterations, right? So this is like a kind of terminated version of the policy evaluation. And this is what I have written here, terminated form of policy evaluation, right? So the terminated form of the policy evaluation is exactly like what we had before. This is the policy evaluation, exact same thing. The only difference is in line 7. In line 7, you don't wait till your algorithm converges. Like the new value is exactly the same as the previous value. So you're going to, if it happens soon, well, we're going to take it. If not, we are going to just do it for a maximum number of iterations, right? This is always the case when you implement any iterative algorithm, right? So you're going to have a maximum number of iterations you give to it, right? And if you do that, as I said, what you get out of this algorithm, there is no reason that this guy is necessarily the value function that you want, right? It could be that guy if it happened really in line 7, you really have the first constraint happening, but it could happen that you have an approximate version of that, right? And if that happens, then what you need to do is to just take that one approximately. Now, and you put it back into this algorithm, right? So you're going to get this approximated value, and then using that approximated value, you can still improve your policy, right? You improve your policy with this approximation, you keep on going, it is going to converge. It is going to converge most of the time. So this is what we call a generalized policy iteration. So you are eventually going back and forth between policy evaluation and improvement. But when you are doing the evaluation, you don't really need to evaluate exactly your policy function, value function. You can just do it up to a specific precision, right? And what you can think about it is of this form. So you could say that, okay, I start with one policy and I evaluate it, right? But the evaluation that I get is a bit noisy, right? It's okay. I'm going to take it and I improve my policy, right? So I improve my policy back, I get to a new one, right? And for this new one, I again evaluate. Again, I have to terminate my evaluation because I cannot do it forever. Again, I get a noisy version of evaluation, but it's okay. Now, typically what's going to happen, the level of the noise that you're going to see this time is going to be lower, okay? And then, again, using this approximated value function, you again improve. You keep on going till you see this jump, this imprecision, inaccuracy in your approximation is very small, right? And you eventually end up with the optimal policy. Everybody's clear? Questions? No question? Okay, so if you got no question, one side note, is there any guarantee that GPI, generalized policy iteration, converge? Yes, there are a bunch of proofs for that. For example, I put you here a link. This is a quite old proof by Tim Mitchell. Do you know him? Who had 1513? You have a textbook on machine learning, right? One of the textbooks is by Tom. Okay, so the guy is quite well-known person, right, in machine learning. So he has one note on the proof of the generalized policy iteration to converge. Okay, you can take a look at that one. If you click there, you're going to see that proof. And yeah, so this is typically the case. So most forms of generalized policy iteration, like if you have this termination of the iterations within the policy evaluation algorithm, even very small, is still going to converge. Okay, but just I put you here as a side note is that, first of all, that proof that this algorithm is converging, it does not guarantee that it's converging very fast, right? It might be still that you need to do the improvement forever, right? So there is no guarantee there as well. But it says that if you just terminate your evaluation, but you just improve forever, then you're going to converge, right? Again, the question is that in that outer loop, when does it converge? You cannot necessarily show it. So there's some specific conditions under which you are going to converge. In some other cases, what you are getting out of your algorithm is an approximation of optimal policy. That is a fair approximation. So numerically okay to take that one and work with that one. Okay?